Hello and welcome again to our channel Artezmia for another video about electronics. Today we are going to make another laser tripwire alarm, greatly improving our previous model that was the topic of our first video. We immediately saw some shortcomings with the first alarm. Most important was the great possibility of false alarms. If a pet, and in my case bats in the attic, cross the laser beam, the alarm will be triggered. And if you want your system to be reliable, you must avoid false alarms at all costs. This was simple enough. Instead of one laser beam, you have now two laser beams that will be vertically spaced by about 2 feet. The alarm will be triggered if and only if the two beams are crossed at the same time. 2 feet is close enough that a burglar won't be able to cross only one of them, but a pet or a bat will not cross the two of them simultaneously. For that, we use two LDRs placed in series and of course two laser modules. Remember, the resistance of the LDR is low when lit and high when dark. In series, low plus low equals low, low plus high equals high, and obviously high plus high equals high. So in order to have a low resistance, the only way is to have the beam on at all times. The other improvement we have that when the alarm is triggered, we now have a siren and stroboscopic lights, red and blue. For this, we will make a flip-flop circuit that will feed two relays that will be powered only when the alarm is triggered and for the duration of the alarm, that is, when the siren is on. We will also use two transistors as switches, one for the siren and one for the flip-flop circuit. They will start conducting when the alarm is triggered. It's defined by a positive voltage on pin 3, the output pin of the 555 timer. For the siren, this has the advantage of not being subject to the 200 milliamp maximum output of the output pin by using the 12 volts directly from the power supply. We are now using a dual output power supply. As input we have 110 AC and output 5 volts and 12 volts. The 5 volts will be to power the laser modules and the 12 volts for everything else. The board is much larger than the first one, and the old CD will be too small for this board. I bought some scraps of acrylic 2.4 millimeter thick. This was the only available thickness. It's way harder to drill than the old CD. We broke quite a few bits. 0.8 millimeters, that is 1/32 of an inch, is fine, but for the 555, 1 millimeter holes are better. That's 3/64. The size of the board is 10.5 by 14.5 centimeters. As materials go, we will need a power supply with dual voltage 5 volts and 12 volts, a double relay module 5 volts, two laser modules, one NE555P timer, two 2N2222 transistors, two LDRs, resistors, two value 5K, one 1 mega, one 10K, one 20 ohms with a 2 watt rating. A siren, one 10 nanofarad ceramic capacitor, one 100 microfarad 25 volt electrolytic capacitor. For the flip-flop circuit, we need two transistors BJT, BC547, two LEDs any color, two 220 ohm resistors, two 3.3K resistors, two capacitors, 47 microfarads, 25 volts, two diodes, one N4148. You can actually use one N4007 instead. And optional is a LED any color with 470 ohms that will be placed in parallel with the siren for testing. I didn't do a KiCad schematics for the circuit. I directly drew it in Inkscape. I did, however, test my circuit on a breadboard before committing to the acrylic. Here's the top side of the board. As you can see, the principle is the same as the circuit that was described in the first video. The alarm is triggered when the two beams are crossed simultaneously. Then the output of the 555 commands the two transistors, one for the siren and the LED, and one for the flip-flop circuit. As our relays are 5 volts, we need 5 volt for the flip-flop circuit. We cannot power the flip-flop circuit with a 5 volt line of the power supply. The 2N2222 transistor has a drop of about 1 volt between collector and emitter at saturation, that means when it conducts. Plus, with the voltage drop through the flip-flop circuit, we wouldn't have enough voltage to power the relays. We have to use the 12-volt line instead and step it down to 5 volts. To do this, we use a 20-ohm resistor rated 2 watts. We certainly could use a voltage regulator that would be a lot more efficient. But anyway, the alarm is not supposed to be triggered often, so the loss of energy is not that important. Make sure to have a 2-watt rated resistor. A common 1/8 or 1/4 of a watt will blow in magic smoke. Here's the back side of the board. Red wires are for 12 volts and 5 volts, green ones are for ground, and yellow for everything else. For the strobe lights, we're using cob LEDs, 30 watt, 110 volts, that don't need drivers, and we need a heat sink even though the LEDs are not lit all the time and don't use the full 30 watts. We tried without the heat sink. They get quite warm, and as a matter of safety, it is better to use a heat sink, but not absolutely necessary. Now I'll show 2 clips. The first one is my breadboard model, powered directly with 12 volts and without the laser modules. I trigger the alarm just by hovering a ruler above the LDRs. The second clip is the actual board without the siren but with the LED and resistor in parallel. Also, I modified the values of the resistor and capacitors on the breadboard to have a short duration of the alarm when triggered. You can really appreciate that a breadboard is not suitable for a working environment with all those cables. We're not using laser reflections on the LDRs to trigger the alarm since we're working on our bench. As in the previous clip, we just hover a ruler over the LDRs. Now, in this third clip, we added the siren, and we also use the ruler to trigger the alarm. As we can see, it is only a half success. The siren is getting most of the power and our flip-flop is failing. Why? Well, the answer is obvious. The power supply is not giving enough current to power both the siren and the relay module. We will now replace the power supply with the standard 12-volt 1-amp power adapter with a barrel jack, like in my previous model board. Obviously, we have to forego our 5-volt line, and we will not be able to power the laser modules. So as before, we will trigger the alarm by hovering the ruler over the LDRs. It works fine, both the siren and the strobe lights. In any case, we have to improve the model. The board is way too big to be practical. We're also wasting a lot of energy by reducing 12 volts to 5 volts to power the flip-flop relays and the relays with a resistor. We could replace it with a step-down module that could also power our laser modules. We could also replace our standard transistors, BJTs, that is bipolar junction transistors, with MOSFETs, that is metal oxide semiconductor field effect transistors, that are much more efficient. These improvements will be the topic of our next video. Thanks for watching this video. If it was of any interest to you, please hit the like button and subscribe to our channel. See you next time for an improved version of this model.